Okay, so when it's asking us to find the extrema of the graph, extrema means maximums and minimums. So what we're looking for here is wherever the graph hits a peak, it's going up and then starts going down, or it hits a valley where it's going down and then it starts going up. So here we have a peak and a valley. This is a maximum and a minimum. Those are the extrema of the graph. Anywhere else where it hits it would also count. And here we go. We just find the coordinates and classify, meaning is it a relative or absolute, whatever. So the coordinates are, in this one, we estimate, looking down here, looks to me like it's around 0.2 or so, but it could be many different things. But you're estimating anything between, say, 0 and 0.5, I would accept, because it does look a little bit closer to 0 than it looks to 1. So this would be 0.5 or 0.2, comma, and then the y value looks to be about 9.5. And this is a relative maximum. Remember, a maximum is where we hit an upside down U shape, we hit a peak, and it's relative because over on this part of the graph, it goes up forever. So there are much higher points on this graph than just this little one right here. But it does hit a maximum, but then it starts to go back up again, and then it goes past that. If it never ever went past that, like say in this one, in this graph, if it starts and continues to go down, this would be an absolute maximum because it never gets any higher than this point right here. Here we have the relative maximum is this point right here. So just to clarify where we were at, this is the answer. 0.2, 9.5 is a relative max. And right here, we're looking for a relative minimum because there are lower points way over here. This is a relative minimum at 3, 0. Relative minimum. Give the coordinates and classify the extremity of each graph. We've done what they asked. We gave the coordinates of each one, and we classified each one. Remember, absolute would be there's absolutely nothing bigger or nothing less than this one. Whereas relative is, well, it does eventually get bigger or smaller, but in this particular area, it still looks like a minimum or a maximum. All right, we're done with that one. Let's go to the other page. Put this in markup, and then you can see me do numbers 7 through 13. All right, for number 7, identify the intervals of increase and decrease. So I'm looking for where is the function going up and where is the function going down. If the function is going up when I move to the right, then it's increasing. If it's going down when I move to the right, then it's decreasing. And remember, this is all with the idea of moving to the right. So if I'm a person standing on this, I'm going to actually draw my person so that they're at the very beginning, as far left as they can go, which I guess if I'm traveling along this puts me way up here. That's where my person is. And if they start walking this way, they're going to fall straight downwards, almost straight down. So if I start here and I start walking, I'm going to be going downwards. So we start on a decreasing interval. Well, that means it's decreasing all the way from negative infinity, because no matter how far back to the left you go, you are still decreasing. And then where do they stop decreasing? Well, right here. And this looks to be at x equals -1.5. And that's a decreasing interval. Then after that, it has to start increasing. So I go back to my increasing intervals. Put one up here. It starts at -1.5. And then it goes up. -1.5, that's the x value. And it goes up, and we see what x value does it stop. And remember, I'm thinking x value, does it stop increasing? That would be right here. Because after that, it starts to go down again. So it's increasing from -1.5 all the way up to x equals 1.5. It's right around there. Remember, we're looking at the x values, not the y values. After the 1.5, it starts to decrease again. So here we go, 1.5. and then it decreases all the way off to infinity. It never stops. It just goes down forever and ever and ever. So this is negative 1.5, comma, infinity. Again, we are concerned with the x values, not the y values. To be clear, let me color code this. So we've got the negative 1.5 up to 1.5, 1.5. So color coding this to make it a little easier to read. Again, I'm not deleting my answers just for the sake of deleting the answers, but what I am doing is showing you a color-coded way to look at it. So maybe we start with green. That's this interval, decreasing from negative infinity up to negative 1.5 with a closed bracket there. This is a bracket, not a parentheses. Then increasing in the red here from x equals negative 1.5 up to positive 1.5. And then in the blue, my decreasing interval, which is there, and that starts at x is 1.5 and never ends. It goes off to infinity. So those are my 3 intervals of change. This one is very similar. I'm going to color code that with red at the beginning, and then it hits a peak and then starts to go down. So in blue, I have my decreasing intervals. So my decreasing interval goes from, because this is going downwards to the right, goes from x equals, that looks like it's 2. So starts at x equals 2 and goes off to infinity. And then in red, it's increasing over here. If I go to the right, I have to go up the hill. And it increases all the way from negative infinity, because it never actually stops being in this red portion where it's increasing, up to x equals 2. Remember, again, we're looking at the x values. So I'm not concerned with the fact that it stops up here. I am unconcerned with that fact. Doesn't matter how high up or down it stops. What matters is the x value. We're looking at what x values are these intervals on. And it seems like the only division is between, are you bigger than 2 or are you less than 2? And so that looks like this. Increasing here, decreasing there. Identify the types of discontinuity. I'm going to go through these real quick. There are 3 types of discontinuity. There is whole, jump, and infinite. So with this one, the answer is, this is discontinuous. What type? It's a whole. You can see that hole right there in the graph. Location, we only want the x value. We are only concerned with the x value, and that is at 1, 2, 3, 4, 5. X equals 5. For end behavior, as x goes to infinity, f of x approaches, well, I imagine myself as somebody who's walking off into the distance. I go that way, and am I going up or down, or am I flattening out? And it looks to me like this person is going to go way down when they go down that hill. So f of x approaches negative infinity as x goes to infinity. Now, when they do this, the difference is that negative infinity sign, which means we're going to walk the opposite direction. So we are going to walk this way. Now, they might go down, and then they go up, and they go up and down a million times, but eventually they're going up, and it's never going to change after that point. So since they're going up, and it doesn't seem like there's any spot where they're stopping, this value is infinity. So as x approaches infinity, that means we go to the right, we go towards negative infinity because it goes down, but it goes up infinitely when we go to the left. So as x approaches negative infinity, f of x goes to positive infinity. Do a similar thing for numbers 10 and 11. Number 10 is continuous. There's no breaks, no holes in this, so that's great. If that's the case, you can just write not applicable or none for the type of location. There are no discontinuities, so of course they can't be in any particular place. As x goes to infinity, f of x goes to, well, as we walk infinitely off in this direction, it looks like we're going up, so it goes to infinity. And as we walk infinitely off in the leftward direction, towards negative infinity, towards x is negative infinity, the y value actually still goes up. Either way you go, eventually, you're headed upwards. because this is f of x. This is the y value that we're concerned with. As x does this, what does y do? And so both of these are infinity. This is a discontinuous graph for number 11. The type is an infinite discontinuity because it goes up or down infinitely and seems to be hitting a wall right around here. And that x value appears to be halfway between 2 and 6. It's at x equals 4. Asymptote at x equals 4, so that's an infinite discontinuity. Location, x is equal to 4. Remember to include that x equals and no y values for this one. As x approaches infinity, well, I imagine myself on the right-hand branch. I choose that one because I can go infinitely this way from this branch of the function. I can't go on this branch because then I can't go this way forever without having to go up an infinite hill. So I'm going down, and it appears that I'm leveling out at a certain point. And you want to think, what y value am I leveling out at? It seems to be stopping right there. The y value is 0. So as x goes to infinity, f of x approaches 0. If it leveled out at a different height, then whatever that height is, that is the value it approaches. And same thing if we go off to the left. If we go off infinitely to the left, that is as x goes to negative infinity, we're going to level out. We're going to keep going downwards, but so slowly you don't even notice, and at a certain point it levels out towards y is equal to 0. All right, last two. We're on objective 3.7, identify reflection and rotational symmetry and confirm it algebraically. So notes for this. There are 3 types of symmetry. There's x-axis, y-axis, and origin symmetry. X-axis means that if you flip over the x-axis, then it's the same on both sides of the x-axis. Of course, y-axis symmetry means it's the same on both sides of the y-axis. And origin means if you flip or rotate 180 degrees around the origin, so everything goes 180 degrees flipping around like a rotation. It's a rotational type of symmetry. Then it's the same. Well, let's look here and we can confirm it algebraically. So if I start with the x-axis symmetry, if I try to flip this over the x-axis.
Malik Hawkins, please report to the front desk. Your ride is here. Malik Hawkins, please.
I'm not cutting this out. Fast forward. There we go. Okay, so x is this. If I look over here and I try to flip that to the other side of the x-axis, it lands in no man's land. There's nothing there. It doesn't have a reflection over on that side. So it does not have x-axis symmetry. So this one's out. Similar for the y-axis. If I go here and I look across from each other, every other point seems to be ending up in no man's land. So y-axis is out as well. So it's not x-axis, it's not y-axis. Maybe it's origin. Well, if I rotate 180 degrees, let's take this point here, and turn it around, so it ends up over there. Yep, it does seem to be ending up right where it is. And if you can imagine taking this, I would encourage you to literally take your screen and flip it 180 degrees. I can't do that, but you take this, turn it 180 degrees, it ends up over here, and take this piece and turn it 180 degrees, ends up over there. So they end up on top of each other. So this has origin symmetry. Now, origin symmetry, according to your notes, go back into your notes. Origin symmetry happens when you switch x and y. So you switch x and y both to their negatives and see if it ends up with the same equation. So to confirm it algebraically, we're going to do replace x with negative x, replace y with negative y, and keep that same equation. We're going to see if we end up with the same thing. Well, negative times negative is positive. So these two negatives are going to cancel each other out. So it's just x times y equals negative 4, which is the same equation we began with. Since we plugged in x and y being both negative and we got the same equation back, that means that this has origin symmetry. Again, look into your notes for that, but the rule is for origin symmetry, you switch x to negative x and y to negative y. Let's see what I'll write down these rules here. So for the x-axis, for origin, let's do x-axis first. For x-axis symmetry, you swap y with negative y. To check if it has y-axis symmetry, you swap x with negative x. And to check if it has origin symmetry, you swap both x to negative x and y to negative y. And if none of those work, then the answer would be none. And what you're doing is taking those and plugging them in to the original equation and seeing if you get an equivalent equation back. Does it simplify back down to the exact same equation or not? Determine algebraically if the function is even, odd, or neither. Just a reminder, even means y-axis symmetry. You can put this in your notes. Even means y-axis symmetry. Odd means origin symmetry. And neither, of course, means none of the above. You might ask, why is there no one for x-axis symmetry? And that's because functions, that is, things that pass the vertical line test, cannot have x-axis symmetry. Because if they did, then when you flipped them over, they would, for example, if you had x-axis symmetry on this one, now it doesn't pass the vertical line test since it hits these two spots. So even or odd is y-axis or origin, and those are these tests. So if you want, you can check x goes to negative x, or you can check both. Well, let's do one or the other. We want to check this algebraically. Now I'm looking at these exponents. Those are even, which leads me to believe this function is probably going to be even. So let's check if it's even by setting even is y-axis, x to negative x. So we'll put in negative x, and I'm going to change f of x into y. Negative 3 times negative x to the fourth plus 7 times negative x squared. Notice every time I replace x, I put it in parentheses. But whenever I take a negative number to an even power, that negative is going to get erased, which means this is the same thing as negative 3x to the fourth plus 7x squared minus 1, because there's no odd powers in here, so there's no way I'm going to multiply this an odd number of times and then end up with an odd result. So this, take a look at that, is exactly the same as what we began with, which means this is an even function. If they say describe the symmetry, well, the symmetry is y-axis. If it had turned out that it was odd, by replacing, let's say it didn't turn out to be even, but then we replaced y with negative y also, and it turned out, oh, this actually is symmetrical with that, then it was odd, then it would have origin symmetry. And if we did both of them and we never ended up with the same equation again, then it would be neither, and it wouldn't have any symmetry necessarily. I'll do one more example of this just to make sure that y'all can see what it looks like when you have an odd function. But pretty much we're done all the examples here. So let's say I change this to be 3x cubed plus x. This is going to end up being odd. Let's see how. Well, if I set y equal to that, now I'm going to replace it with negative x. This is negative 3x cubed minus x. And remember, when you have an odd power, since you're multiplying by a negative an odd number of times, it's going to go odd, even, odd, even, odd, even. On odd numbers, it's going to end up keeping that negative. It's going to cancel out if you have an even power. So this, you may notice, is not the same as this, and so it's not even. But you may notice it is the negative. It's the exact opposite. Because this is become negative and this has become negative, whereas in the original, both of those were positive. So if it has become the exact opposite as to what it was before, that makes it odd. The exact opposite to what it was before makes it odd. If it is the same as it was when you replace x, then it's even. If it's the same except completely reversed, then it's odd, which means this is an odd function. And the symmetry, see if you remember, is origin symmetry. You could also have it be neither. And I'll just show you that example. If you want it to be neither, then say we have f of x equals x squared plus x. Well, we'll plug in negative x to that. So do f of negative x. That is replacing it with negative x. Replacing x with negative x. And then we get, this is even, but this is an odd power because it's a power of 1. So we end up with it canceling out here, but not here. So this is positive x squared minus x. Not the same. Nor is it the exact opposite, because if we reverse it, if we take the negative of that, then we would get negative x squared plus x, which is not the same as this either. So it doesn't pass the even test, it doesn't pass the odd test. It's neither the exact opposite when it gets changed for negative x, nor is it the exact same as it was before. So it's not even and it's not odd. Here is where you can tell it's not even, and when you take the negative of it and see it's not the same either, that's when you can tell it's not odd. So it would be neither, and there's no symmetry for it. All right.